with Xinchen. Christina, any thoughts?
Yes. So the topic, okay, the stop search in the compressed region via semileptonic decays is based on the recent paper we posted. All right, so we have our collaborators here. So the title right here is, okay, you can see that it's a CMS and R plus ATV exclusion plot for stop search. All right, so we can see the nice big bulk here. People usually talking about this region. Okay, they said, okay, the stop is being excluded till here. All right, but obviously we have, okay, several gaps in this two-dimensional plot. Right? So here the vertical axis is the LSP mass, or here is the stop mass for both plots, but we will go to details later. So we move on to the motivation part. So right now we have relatively light Higgs, 125 GeV Higgs, right, which puts tension on naturalness, and generally speaking, for supersymmetry model, you have to go to some specific region of sub-breaking mass, etc. Okay, to get the light Higgs mass. All right. In this scenario, a light stop is preferred, right? Because we know that the scalar Higgs mass should be cancelled by the stop loops, all right, around TeV scale to be
probably the table. Probably the cable.
The connection?
Which could also be the reason for the, as you're jiggling it, it seems like the brightness is getting better
Or the
sometimes
color
too.
maybe.
the color. Yeah, the color goes back. Okay, so
The bulb is getting near the end of the slide.
No.
Could I ask you to just move over to this side, because the way the room's set up, we can provide some, let's see, there's even some light for you. If you stand over here instead of leaning on that, you're not blocking the big guys that are over in the summer room.
I'll try. I'll try. All right.
So you can stand on that side.
Yeah,
yeah,
that's
but-
most efficient.
Yeah.
Cool. The connection.
Okay, hold on. So, okay, as can be seen from the previous exclusion plot, okay, right here, okay, it's been excluded, all right, if the LSP mass is below around 300 GeV-ish, or 250, all right, then the stop mass has been excluded to very close to the sub-GeV mass, all right, it's like already 700 GeV. So, all right, and the traditional search techniques, okay, you can find in the previous plot and the many reports, okay, using many kinetic variables like, okay, these are not sensitive for the stop in the compressed region, okay, but what I mean compressed region is the region that, all right, the mass of the stop is about, is very similar to, all right, the top mass and the LSP mass, all right, the sum, all right, becomes the stop mass. Okay. I will explain, okay, the reason why, okay, later on, but you can see, okay, this is exactly the gap we get right here. There are also other gaps, but we are not going to discuss them today. All right, so we need, okay, it's very, okay, one very apparent motivation for the work is that, okay, we need to fill the gap, right, because just right now, currently, there's like no constraint at all. All right, so also, all right, so the topic of our work is the stop search via semileptonic channel. So why do we emphasize the semileptonic channel? So why do we prefer semileptonic decays? Okay, what's the merit of this channel? So of course, less standard model background. Okay, especially okay the QCD multi-jet background, because in a high energy collider like say a 13 TeV LHC, all right, this is like hard to get, okay, at least from simulation. Right? The experimentalists might get this from extracting from their data set, but for theorists or who having only computer, then it's like hard to get from Monte Carlo simulations. Also, it's the the cross-section is considerable, okay, compared to the fully hadronic decay of stop pair and the dileptonic ones. All right, we can see, all right, for compared to fully hadronic decays where the 2W from the stop decay, stop pair decay, all right, become decays hadronically, we have a branching ratio around 46%, right? While the dileptonic decay, all right, so both W decays to lepton and a neutrino, right? So you get 2 lepton and 2 neutrino in the final state. The branching ratio is only 11%, right? So for semileptonic decays, the branching ratio is around, like say, 43, 44%, right? If that's correct. But so it's comparable to fully hadronic decays, right? But it's definitely bigger than dileptonic decays. So we, okay, it's like, okay, at least from cross-section point of view, okay, that's preferable, right? And also it contains more information, all right? You have a lepton, all right, except for a bunch of jets, B jets, okay, and the missing energy in the final state, right? Of course, the first thing is, okay, lepton is easy to detect, right? They have high tagging efficiency. Also, the momentum resolution is higher, especially compared with jets. And also, we can utilize kinetic relations. All right, so compared to a bunch of jets, okay, a lepton tells you is more information, all right, via kinetic variables. Okay, and this will be discussed in detail. Any questions so far? All right. So the outline is quite simple. Okay, I would explain the kinetics in details and explain. Okay, for case study. Okay, we have a benchmark point. Right, for stop mass. All right, then we go to the simulation and the following analysis, present the result, and then come to the conclusion. It's a very rough outline. All right, so the first thing is the stop decay. How stop decays in the compressed region. All right, of course, in compressed region, all right, when the stop mass is about the top mass plus the LSP mass. Okay, it's most natural to assume our decay topology looks like this. All right, so we have 2 stops decays from 2 stops generated from gluon or maybe other subleading PDFs. All right, then we have each stop will give you a top quark and an LSP because SUSY is like in this case is still R conserving, so you would have supersymmetric partners, show up in pairs in each vertex. Right. So you finally what you got is a top pair plus an extra pair of LSP, which is undetectable in LHC. Right. You can see them by in a way of MET, but not explicitly seen that. So. So what happens, when we close to the compressed region is, so in the stop reference frame, when a massive stop decays into 2 objects, right? One is top quark, one is LSP, they become static, in that frame because you have no energy left. Right. So when the stop is produced with a boost, then the 2 static decay products, after this will become co-moving, in the lab frame. When I say co-moving, means they share they're just moving together. They stick together with sharing the same speed. And it's almost trivial to get such relation. So their momentum. So here's the LSP momentum p chi over the momentum of stop. Simply follows the ratio of their mass, and this is like say the first key point of our analysis. So we should keep this in mind. So when the stop pair is produced near the threshold, or not far away from the threshold, they're nearly back to each other. Then, so we have a pair of these LSPs, which is undetectable, and then they also become back to each other, and leaving less massage, in the MET, really leaving a relatively small MET in another way. Then what we got is, a top pair, which is dominant. Right? It's very common in 13 TeV colliders. So that's like say one simple explanation of why the gap is not closed. Right? Why CMS atlas people cannot find it till now. All right. So, all right. So how to solve it? Okay, we go to another way. All right. So compressed region with an large initial state radiation jet. All right. So here's like say draft I draw for this kinetic setup. All right, so we can see, all right, if the stop is not just generated in pair, but with a very hard radiation. All right, so we have a jet. Okay, so let's call this PT JSR right here. So, okay, we have a simple relation, right? Because we have three objects, right? Three body. Okay, in this level we have okay, probably this is too small, but okay, this is the stop one PT. All right, let's call this the PT plane. All right, this is the PT of the first stop and the second stop, and then this is the JISR, and they sum up should be zero. Right, the transverse momentum conservation. All right, then all right, so the momentum of PT so let's do this. All right, so the transverse momentum sum of the first and the second stop, right, should be negative. Right, should be some vector pointing this way, negative to the PT ISR. All right, and recall that the mass relation we have right here, they follow the simple relation, right? So each of the LSB just carry a portion, right, a fixed portion of the PT of stop right here. So what we got? Okay, so finally we have the contribution or the sum of the two LSPs just basically opposite to the PT ISR direction, and their size should follow a very simple relation, right? They're fixed by the mass relation, the mass ratio. Right? If there's no other source of MET, like let's say, okay, all these stops, okay, then decays to a top, and the top decays to, like say, a W boson and a B, and a B jet just detected. The W boson decay hadronically. Also, all get by the detector, no other source of MET, then all right, this will follow the simple relation. This is like say the basis of okay the recent hadronic analysis, right? So you have full hadronic decay, and you just simply pick one MET and a very hard jet back to back, and you somehow analyze the ratio, and you got an untrivial peak around this value. Right? This is like the basis of the recent search. Right? So what about the semileptonic case? Semileptonic case, we have one lepton, right, and a lepton produced with a neutrino. Right? So the neutrino, of course, will sum up. Okay, like say, okay, let's forget about the stop so far. Okay, let's say the stop is like somewhere just gone. All right. So we have this is again, all right. So because the relation still holds, right? The relation still holds. We're still in the compressed region. So the back-to-back relation, the sum of two LSP transverse momentum will still back-to-back with the JISR. But in this case, we have an extra source of missing energy is the neutrino momentum. All right. But okay, so we need to solve it, right? We need to subtract the neutrino contribution from the missing energy, so we can get the ratio again, recover the ratio again. So we need to solve it. So right now we have three mass shell relation. Right? We have some inputs, like say the lepton momentum is already known. All right, so that's good. All right, the B jet, all right, can be detected. Okay, the energy you know that all. All right, we have four components of neutrino momentum, but we have three mass shell relation, right? The neutrino itself is massless, all right, and with a lepton, or it should give you a W mass. Also, these three, okay, should be come up from a top mass. All right, so we have three relation, but we have four unknown variables. So what's next? All right, so we need to make some assumption here because we are out of assumptions right here. So out of relations right here. So we need to have some assumption to get the fourth relation. All right. So what's the fourth relation? Actually, it's been indicated from this plot. All right. So let's assume. All right. So the relation we have just mentioned just strictly follows, or we can tell. All right. So right here, the PT from the neutrino would have no perpendicular component to the PTJISR. Right? So they are completely back to back. Let's hold this. All right. Then, all right. So if the missing energy, all right, have some component which is not exactly back to back with the hard jet, all right, then what can we assume? All right, we would simply assume that's coming from the neutrino contribution. Right. So the neutrino, so we can get the neutrino exactly. We can get one neutrino transverse momentum from this assumption. So what can we see in the detector is we have a hard jet and an MET this way. All right. Then we just take the perpendicular component here and assume, okay, this is our neutrino momentum component. We get one component, so this is the fourth relation, right? So we have four equations, then we can solve for the whole momentum of neutrino. Okay, then after solving this, okay, what we have? Okay, we already know the parallel component of the momentum. Then okay, we can subtract that, right? We can take this one and subtract these two, right? Then we can recover the such mass ratio here. All right, and for standard model background, this one should be around 0, right? Because this is coming from some measurement error in the calibrating the PT ISR. All right, so we have the idea right now. We have the idea. We know how to do. Then why not just do that? Because okay, in actual simulation, there are like say a lot of other problems will just come up. Okay, so we choose the stop mass to be 400 GeV. Okay, to be conservative. Okay, it's not very heavy, nor very light, so it's like okay, intermediate mass. Okay, worthwhile to look at. Okay, so we have. So these two, you can say the mass gap is about the top mass. All right, so we are sitting exactly in the compressed region. Okay, and we need to compare. What we need to compare is the standard model top pair production. All right, this is our main background. So the first thing is we look at the lepton energy. Okay, so we have. Okay, so let me explain what these two plots mean first. Okay, so at first, okay, this is, okay, maybe it's just too small, but this is the logarithm, okay, the logarithm of the energy of the neutrino, okay, we get from the bottom level. Okay, you just, like say, get this from the LHE file. All right, so we can see the neutrino, okay, by just looking at the file, and also comparing it with the lepton energy we got. Here we only comparing semileptonic decay, so there will be only one lepton and one neutrino. So we can just have the ratio. And after taking the logarithm, okay, if the decay of W is fully symmetric because the lepton and neutrino are all massless, okay, in the high energy limit, right, then okay, this distribution should be symmetric, right, around 0. Because the chance of a lepton will have high energy and the chance of a neutrino will have high energy is just the same. All right. Here we have a tiny asymmetry here, but this is just because of the spin correlation. But as you can see, it's not dominant. All right. So they are still approximately symmetric with each other. All right. So on the left, the plot on the left is just okay. Just the distribution for the background, okay, the standard model background, and this is for the signal. All right. So we can see that okay. So this contour here, okay, this is before we put any missing energy cut. All right. So before we put it, just naturally show up there. Then okay, it's basically symmetric. But after we put, okay, the resolution is okay, not enough. But okay, after we put an MET bigger than 200 GeV cut, all right, then what are we doing actually? Okay, for the standard model background, we are forcing one of the lepton to have a high PT, right, to get such a big MET, right, because okay, the error is okay relatively small. Then if you get a really hard MET, basically one of your neutrino becomes hard, all right. Then okay, this pushes, all right, the ratio, okay, the logarithm of the ratio, okay, to this end, okay, the energy of the neutrino goes higher for the background, all right. But for the signal, since we have extra contribution, we have LSP, right? So the impact on the signal is okay. That's fine, right? The signal still looks okay, not very asymmetric here. So we really want this MET cut right here. So basically makes the background and signal difference. All right, we choose the MET cut to be bigger than 200 GeV right here. Also, we choose the solution because previously we have a quadratic equations. Right? We have four relation, and the four relation they have mass shell. They have quadratic terms. Okay, in principle, you have two solutions for the neutrino momentum. All right, so we choose the solution with a bigger neutrino energy. All right, so here, right, it recovers the background so well. We can see that later.
Question?
Yeah.
What's approximately, do you know the efficiency of this cut? What percentage of your signal passes this net cut? Do you know that?
I haven't just explicitly looked at it.
Do you know, is it very efficient? I mean, is it like?
It's very efficient.
It's not,
Yeah.
not 1%, is it like 10% or?
For the signal, most of them can okay, a significant portion of them then can get through this cut, but for the background it cuts like say many backgrounds.
Sorry, can I ask a related question? So just to understand, the left plot is standard model TT bar?
Yes, standard model. Okay,
With extra jets. I mean, I'm just trying to.
it's we haven't go to the ISR jet part. We're just comparing.
So this is without extra jets.
Yeah.
I see.
Yeah. So
Okay.
it's just comparing the natural the distribution of the neutrino and the lepton energy distribution. All right. Okay. Another thing we need to concern is the azimuthal distribution. All right. We have a bunch of we have B jets. All right, but they are not of our concern so far. So let's still focus on the lepton. All right, and the neutrino. All right. So in this case, the MET and the PTJIs should still be close to back, right? Even in the presence of the neutrino, all right? They still should be close to back, at least not co-moving together, right? Which makes our analysis less worthy. So we put the angular the phi difference between them should be bigger than 2, right? This is just. Basically, all signals follow this. Right? Most of the signal will follow this rule, so that's okay. Right? So what's the relation between the lepton and the MET? All right? So we know that the energy, the neutrino would get higher energy, right, for the background. For the standard model background, we have high energy if we put the hard cut. Okay, what else? What's the azimuthal distribution difference? So the standard model, you have a high MET, right? Basically mean you have a high energy, high PT neutrino. All right, that also means your W boson, right, before the decay is somehow boosted, right? It's hardly boosted, hard boosted, in the PT plane. All right, then we can come, we have the impression that the lepton in this case, right, the leptons in this case should be very close, right, because they're highly boosted, and they are somehow co-moving together, right? But for the signal, they are not. So we should cut the lepton and the MET, and we should cut the phi difference. Right? Does that make sense? All right.
But sorry, just to make sure. When you say signal,
Yeah.
you already are including a hard jet emitted. You're not. So.
Yeah. So
the signal.
right here is
defined
already
by-
ready with
Okay.
the.
Okay. It's just, okay. No, because there was no. Okay, thanks.
Yeah, but I should just.
No,
Yeah,
it's
this
fine.
is.
Thanks.
So Okay, so the left plot is for, like, say, people with good eyesight, all right? And I just want to show up right here. But you can, this is already, I have solved some R bar M distribution right here, all right? So R bar M is, like, say, the recovered ratio, all right? They should just be, you should find, okay, the distribution or a untrivial peak around that mass ratio. But let's put this aside, okay? Let's just go to the one-dimensional distribution here. So right here, the green curve is the semileptonic TT background. All right. Okay, you can see that the distribution, the delta phi of the lepton and the MET, okay, is centered at 0, and it's dropping pretty fast. Okay, they are really co-moving together. Right? They tend to be close to each other. Okay, because WJ in this case is like highly boosted somehow. Okay, but okay. Also, we would have red curves of points right here, okay, which is the dileptonic TT background. Right? There's like some chance you haven't tagged another lepton, right? So both top can give you a lepton, but one lepton maybe is because of the isolation rule, okay, it's been eaten by some jet, right? Inside the jet by chances, right? Or just higher with a higher eta, it flies out of the detector. So chances are there. So if we look at the blue one, which is our semileptonic stop pair, which is our signal, and the red one, they are really close together, right? By this method, you cannot separate them. All right.
So you do have a second lepton veto already.
Yeah, we have a second lepton veto already, but this is like relative distribution, and because of, okay, another lepton can be missing, right? Because isolation rule or whatever. So it will appears like a semileptonic, and we need to take that into our consideration.
So this is normalized?
Yeah, this is normalized.
Because it just kind of looks like, I mean, even with a lepton veto, the dileptons are still pretty, I mean, even the total rate is pretty large.
I think
It's not just
to one.
Yeah, it's normalized to 1.
Oh, so it's not, okay.
It's a fraction of the event.
That's what I would call unnormalized, but that's okay. I understand. So.
Yeah, so we will see later this dileptonic's really some troublesome, and we tried many ways to get rid of it, but okay, in generally speaking, because you have an extra neutrino, right? So this is the extra source of MET, so it somehow looks like a stop signal. So in principle, there's like no very good way to just separate them. Alright. So this is like the cut selection, okay, after like say many trials, alright. So we have at least some jets, alright, because that's TT decay, alright. The events with tau jets, alright, just vetoed because tau jets you have extra neutrino coming from that, okay, that pollutes your MET. Also, there are other cut. Okay, our PTJSR cut is 475 GeV right here. It's pretty hard. We have this I already have mentioned. Okay, so we pick a greater ET among the two solutions, E nu for two solutions. Okay, for the solved neutrino momentum. Okay, if it gets too high, that basically means it's like somehow physical. Maybe with some error makes that very high. Like say you have 1 TeV PT of neutrino. What does that mean, right? It's kind of okay unphysical. So we put a selection rule, okay, somehow on the PT of the neutrino we have reconstructed. All right. Also, okay, if we go back to this, all right, you can see, okay, no matter what, okay, we don't want this region, all right. So the most of the signal still stays in when their ratio is not that big, all right. So so the neutrino momentum should be, okay, the ratio of neutrino momentum to the lepton momentum should be less than 6, all right. Also, like say, I have tried several times, right, and this is like somehow optimized cut. We can have more than one B jet, all right. We have at least one B jet to get the mass shell, but also you can have 2 B jets. All right, and if more than one B jet can give you the solution, then we choose the one that can give a smaller R bar M. All right, so we have background in the signal simulation here. Okay, so this is like the method that everyone is using. All right, so the main background we are talking about is the semileptonic TT bar and the dileptonic TT bar. All right, the fully hadronic, because you cannot give a lepton, so it's just been dropped. Right, we also have simulated and considered the single top production. Okay, which is also could give you some some kind of, but the cross section is just too small, and it's not in our signal region. Also, these two, the multi-vector boson, or vector boson with jets, and also the TT production with an extra vector boson is just because the cross section is small, all right? And also they cannot give you a good solution. Then they just not show up right here. Actually, they give you only few events. All right, so we do not consider them right here. Okay, for the signal, we have stop pair which decay semileptonically. All right, so here's the result for case study. All right, so here is the green one. I hope you can see the greenish here. Okay, so the green one right here is the semileptonic background. All right, so what's the purple red color right here? That's the dileptonic one. All right, so which is somewhat surprising, because we focus on eliminating the semileptonic background, right? The semileptonic top pair background, but in our result, the most prominent background is the dileptonic one, right? Because as we can see in the previous slide, all right, so there's like no very good result, all right, up to now. Okay, we cannot just tell this from the signal. All right, so this actually is the main body of our background here, and here's just the signal. Okay, you can see the peak around 0.6-ish, which is around the theoretical prediction of the RRM should be.
Somehow that's because the dileptonic has your cuts are sort of using the fact that for the semileptonic there's sort of only one source of missing energy.
Yeah, so you can just
here you have two.
Yeah.
And so the dileptonic has two sources of missing energy. So these,
Yes. Exactly. So people are doing hadronic analysis before this work, and what they are doing is much simple, much easier than what we are doing here. So because they would just choose ISR which very high GV, because they really don't want many subleading standard model, like say vector boson and QCD whatever. So they choose a high PT cut for the JISR. Then they pick a very back-to-back. You can see the phi difference. Minus pi is just 0.15. So it's really back-to-back MET and hard jet. All right. So and then they compare the ratio, and of course at least one BTEC to make sure that's coming from the stop. Okay. All right. And you can see. You also so you can also recover this peak for the signal right here around the theoretical RM value. But the background is much bigger, because in this case, so this is like the mix-up of all the backgrounds. You can have, of course, the true fully hadronic TT, right? Also, you have semileptonic, while one lepton is just going nowhere. Then you have a fake fully hadronic TT background. Also, dileptonic can get in, but we do not have that source to generate them separately, so it is like the mixed background. But this is like TT for all kinds of decay.
Yes. I just was coming back to going back one slide. So this case here, I was just wondering about the dileptonic background.
Yes.
So the difference between one important difference between the dileptonic background and your signal is the dileptonic background is made out of massless neutrinos, right? Whereas I'm thinking of the missing energy is made up out of two massless neutrinos, whereas in the other case is a massive one. So is it possible to use something like an MT2-like variable, which is kind of the minimum
Yeah, we
mass.
have tried.
The minimum mass of the, yeah, you know, the minimum mass of the, you call one of them the LSP, give it a mass, and there's some minimum mass for that, right, that can explain the event.
We have tried something like that,
Yeah.
but it's like the result is not that good. Okay, or we need to put much more time in that. Okay, so up to now the results on this dileptonic analysis is not optimistic. All right, so we choose to just focus on the semileptonic analysis. Right?
No, I don't mean redo it for the dileptonic case. I'm saying, I'm saying, could you try to find some additional cut to beat down the dileptonic background, which is now your dominant background, right? So for this search, for the semileptonic decay mode, TT bar dileptonic is your dominant background.
Yes.
So can you find, so I'm asking, is a way to try to make
But
a
you don't
cut
see
for that?
right? So how do you use MT2?
No, what I'm saying is that, so you can't literally be MT2, but I'd have to think about it, maybe it doesn't make sense, but the idea behind MT2, right, is that there's some minimum mass, right, that can explain the event.
Standard for the mass difference. Mass, right?
Yeah, so you're saying it's even that is not sensitive here. Okay.
We can discuss this later.
Yeah, sorry. Thanks.
Okay, so the significance, all right, so needless to mention, I mean, you can see that, right, so the scale is about the same, but, okay, the significance you get right here is, like, say, it should be much smaller than this one. You have a big bulk right here, while this one is relatively small. Okay, so, okay, what about, okay, the next thing is, okay, we have done one benchmark point, okay, which is 400 GeV. So what if we move along the compressed region? Okay, if the RM bar, okay, so we have reconstructed from the event, okay, exactly follows the mass ratio. All right, so we have tried, and you can see, okay, so we just randomly picked 3 different masses. All right, so it could be from 300 GeV stop mass to 700 GeV stop mass. All right, and okay. The vertical line is just the expectation, all right, you get from just calculation, all right, and you get the distribution, okay, the center bed is falling pretty good, right? So you're moving along this, so our construction makes some sense at least, okay, we are actually reconstructing the RYM, not anything else. All right. Okay, so we move along the compressed region, all right, so if this is okay, maybe I'll show that later, but if we move away from the compressed region, what if the mass difference is not exactly the top mass? Okay, what if it's, like, say, higher or smaller? So there are 2 sides, and the many details, okay, I maybe do not have time to explain detail. Okay, if the neutralino mass is higher than the stop mass minus top mass, all right, that basically means the neutralino, okay, so you have a stop mass, all right, and the portion of the neutralino is too high, so the rest of the energy, the mass is not enough to produce an on-shell top. So in this case, what you get is, like, say, the top would become off-shell, all right. But the off-shell top, all right, if we not exceed another limit, okay, so the off-shell top will still decay to an on-shell W and B jet, right. So we have. Okay, maybe it's going too far. Okay, so these 2 mass shell relations still hold, right? We still have an on-shell W. We still have on-shell neutrino. Okay, and also, like, say, this still holds. Okay, the transverse or the perpendicular part is still the same. All right, but all right, this one never holds. Right, but this one is, like, say, being busted, right? Because it's not exactly the top mass, but the mass difference, or you need to calculate. Okay, but there's some error. But also you benefit. Okay, so one of our 4 relations break down, but also, okay, this one would have higher ratio, higher M chi versus over M stop ratio. All right, so you can see, okay, so this yellow part, all right, okay, it's moving. Okay, of course, it's, like, say, not as narrow as this peak. All right, so we are choosing 350 as an example. All right, so but it's moving. Okay, you can see this like tension. The potential of the whole peak is moving this way. Right? So your benefits from a bigger IM bar expectation value. All right, but okay, the worst thing happens when the M chi becomes too light. All right, that means this is not compressed anymore because when the stop decay, then it can decay to a chi and the top with some extra energy, right? So they will produce with some PT even in the stop rest frame. All right, then the compressed region. All right, so our assumptions and the many of the kinetic relations never hold. All right, so you can see that, okay, just 30, okay, yeah, the resolution problem, sorry. All right, but if the chi mass is just 30 GeV lighter than what it should be, all right, you can see the peak is much lower. All right, then, okay, this is not, this is actual distribution. All right, so this is not the fraction of the events. Any question? No? Okay, so we go to the statistic part, okay, because we have simulated all the background and the events, okay. So for the signal region, okay, so we define if the neutralino mass is, okay, in the center of the compressed region or heavier than that, heavier than expected, all right, then we simply choose the IM bar to be, okay, the signal region is defined to be IM bar less than 1 because higher 1 is like have no meaning. What would that mean? And the low amount is coming from the expectation value minus 0.15. All right, it's just a choice. Okay, you can choose another, give you different significance. This one is just we have tried, and this gives you okay the optimized value. All right, at least close to that. So if the neutralino mass is lighter than that, all right, then we choose, okay, another way to define the expectation value of R bar M. All right, just like we can choose that, but generally speaking, we do not expect to have a very good result for this case, right? Because you can see that the whole peak is being collapsed. All right, and the significance is given by the complex, not very complex equation here follows like if the background is distribution like a Poisson distribution. Okay, I don't know if I can handle this part very good because Christina doing is the one who were doing this. So this is the significance we get. Okay, if we allow some systematic uncertainty for the background, right, bin by bin. All right, so if there's like no systematic uncertainty, so that's good. All right, the significance goes high, but if you go higher, okay, so if you have a 20% theoretical systematic uncertainty, then it drops down to like say less than 5. All right, but
so the 20% here or whatever, this number means an uncorrelated error of that size in how many bins, in each of how many bins roughly?
It's related to the number of bins. It's specifically for our, so we have number of bins like this.
Yeah, I guess so something like 5 bins or so.
Yeah.
In each one of them has some whatever percent uncertainty, independent.
Normalization uncertainty. So if you don't have.
It's an overall normalization
Yes,
uncertainty.
overall
Okay.
normalization.
So you're assuming the shape is good, and you just this is an overall.
So
Okay.
apply an overall normalization.
Okay. Okay. Thanks.
All right. So here's our results. All right. So the red red number right here is just exactly our case study we have done before. So what's the significance we got? Okay, from that plot is 8.4. All right, and compared to the Foley hadronic analysis we have done, all right, the significance is about 4, but actually we can just having a hard time to push it to that end. Okay, the most we can get is about 4.
So you assuming what systematic uncertainty?
No systematic uncertainty.
Zero.
It's just like go
Okay.
optimize.
Okay.
So so this line is where we sit exactly in the compressed region, right? So where this mass relation, okay, exactly holds. Okay, so right here we have, okay, when the neutralino gets more, like say, heavier. Right? So this is a heavier neutralino case. Okay, so in this case the top will go off shell, and you can see, okay, in the low stop mass, okay, this is like benefits from a higher RM distribution. All right, so the significance is even, okay, somewhat better. Okay, but this is, I think, it could be explained by some statistical effect. But okay, but when you goes to a higher mass region, all right, so still, okay, where the exact one still wins. All right. So as we have expected, okay, when the exact kinetic relation has been spoiled, okay, when we are far from the compressed region, okay, where the neutralino mass becomes lighter, all right, so they decay with some PT, all right, even the rest frame, okay, the significance you get is, okay, pretty bad right here, right, but that's not the problem, right, so we can see, okay, from the overall results, all right, so here it's like, say, exactly, okay, what I've said, okay, moving along the compressed region, okay, we just simply raise the mass, but keep the mass difference, all right, so the significance is pretty high, so we get about 5 sigma for 500 GB, right here, right. And also for this line where the neutralino mass becomes heavier than this line, okay, so still okay, all right, so the significance is a bit less than this, all right, but all right, you can see that from the table right here, but all right, still works, all right, but okay, the worst thing happens right here, okay, the study is not for them, so the significance becomes really bad, all right, you can see that right here is like not sensitive anymore, but no problem because the traditional searches can cover this region, all right, so
you're really going to close that
Yeah.
little gap, that little
yeah, the gap is
that
like
little
along
wedge
this
or
line.
whatever is, you're going to go all the way into the wedge.
Yeah, so
Anything bad happen if you go all the way
so
down into the corner?
Of course, when LSP mass is 0, then you don't get any.
It's- yeah,
iron
when it's-
becomes 0, and then you are hiding again.
yeah, so that would be some search from the cross section rather than using this strategy. Okay.
Yeah,
You check
so
how close you have to get in mass?
The stealthy stop is still not covered by this.
Yeah, the point you go down the smallest is
250. Like
Yeah.
and if it's too light, then okay, maybe
The
we should.
250, it looks, I mean, that last point, it looks like you're still very sensitive, right? It's red.
Yeah,
So,
right.
so that's kind of why I was asking. So what happens if you keep going?
When you keep going, then
Just not changing anything.
Yeah, so
it's
if
gonna
you-
crap
yeah, yeah,
out.
yeah.
How does it crap? Where does it crap out? I guess I'm asking.
yeah, I mean, but okay, so when you goes back, okay, this peak still there, okay, but it's moving this way.
when RM is 0.2, then it's hopeless, right?
Right. When you're moving this way, okay, of course, because of the cross section gets back bigger, so the peak goes move this way and they go this way, and it was similar to you have bulk of, like say the standard model background, and you have some kind of extra layer on it. And okay, the main purpose, okay, or okay, personally, I'm more interested in higher or heavier mass. All right, and when it goes back, okay, to like say go too downward, then okay, it becomes like okay other search rather than okay. Our main purpose, okay, we can cover it here, all right, and of course exactly this line. Right. We do not worry about this line so far because okay, as the luminosity and the resolution goes up, okay, this will be eventually covered by traditional search. All right. So these two curves are like from the atlas current mount, right? Just like say the title, the plot from the title page. Okay, this is coming from top decays to an on shell top and neutralino, this is neutralino, and the WB search, all right? And then we are doing really well, okay, pretty impressive, at least to me, all right, along this line.
So what would you guess is a reason, so this does have to be multiplied by some dilution factor from your background uncertainty. Do you have a best guess of what a reasonable value is for that? Because this is still for zero systematic uncertainty, right?
Yeah.
So I need to multiply this significance by some number less than 1. Do you have a best guess as to what it is?
Sorry, I haven't. Yeah, so that's like, this is like the final result we exactly show up in that work.
But you assumed, you assumed zero systematic uncertainty here on the background.
Yes.
Realistically, it'll be non-zero.
Yeah.
So that'll be diluted somewhat. I just wonder if you have a guess for what is a reasonable systematic uncertainty.
So we have,
how much it changes that result.
okay, so at least we can have, okay, not, actually we have, right, but not point by point, but just from here to here, right? You can see that it's like for the 8.4 here, for the 400 GeV, okay, you can see how it drops. Right? But,
So I'm asking, where do you have a guess for where you sit on the horizontal axis? That's what I'm asking. Do you have a guess for where the experiments will actually sit? What the background uncertainty will actually be? I mean, if it was 20%, it would.
if it's 20%, then it will go down to, like, say, right here.
Even at 20%, you'd still get down to there?
Yeah. Because that's like exactly what we got, right? So it's like 8.4, and then drops down to, like, say, about 5. This is, like, say, the benchmark point of that.
Okay,
But this,
good.
okay, people are, like, say, trying to play optimistic, or people who are.
Sure, no, I'm not arguing with the plot, I'm just trying to interpret.
Yeah, I know that's fair, but I just like you need to show, okay,
No, I don't know.
the beautiful one.
I don't know. You can just say.
That's why I asked if I had a guess. I
Yeah,
just
I
asking.
don't know.
Yeah, people usually they just get the background and okay, yeah, let's do the S over square root of V. Yeah, ooh, that 5 sigma. Okay, let's put it on the plot.
But this uncertainty would be from theoretical prediction, or is there a way to do this with data?
It's like say the normalization of the background. Something
Right, but
like that.
is
We
there-
already have applied some normalization on the background. It's kind of like say
No, yeah, but what
being
I'm asking-
conservative.
What I'm asking is there a way imaginable to do it with data, or you would have to do it from Monte Carlo? So is this uncertainty that you're talking
Oh, I
about?
think
is
you
it-
would do it from data. They always do it from data.
Experimenters can have their black magic to get this from over there.
But, yeah,
How to
here
do
I
it
guess
from data
it's not
because it's
so.
contaminated by your signal, right? So if you really... Okay, anyway, sorry, this we can just take it.
So we come to the conclusion, all right, so that I hope that the plot can be
That's why we have it
somehow
standardized.
convincing. So basically, okay, we have a wall of words right here, just like they got this from the conclusion of the work. But all right, so basically we somehow try to close that gap, all right, and using a different technique, all right. So previously people are using fully hadronic channel, and they are doing well, but okay, still cannot go to that high. So what they have got is around 400 GeV, all right, also assuming no systematic uncertainty. Okay, at least they haven't mentioned that. But in our plot, okay, so the 5 sigma is around right here. Okay, so it's still some distance, right? So so for 300th inverse frontal bond, okay, it goes up to 500, and then generally speaking, okay, we can change or adapt our mass shell relation. Okay, you can change the m top. Okay, in the last mass shell equation, and you can actually exactly analyze this line, and any line you want. Okay, you can even scan over here, but okay. But this is really covered by other searches, right? So we not bother doing that. But okay, really focusing on this line. Yeah, so that's basically what the conclusion is talking about. So we need a light stop, then okay, then we can go to the light, can come up with the light stop in the compressed region. That somehow soothe the naturalness problem. That's Thanks for watching. I do not have that slide. Sorry.
I mean, just thinking about the background thing a little bit more.